Hello friends, welcome to my channel Civil Smart. Today we are going to design a combined footing which is beam and slab type. We have already done a slab type combined footing, so now we are going to design a beam and slab type. So we have this type of problem, that is column A having a load this much is the size of the column A and the load is 800 kN. Column B of having a size 400 by 400 and the load is this much. Both columns are 4 meter apart and the width of the footing is restricted, in this case 1.8 meter. If it is not restricted, you can assume that the safe bearing capacity is 180 kN per meter square and FCK is 25 and FI is 415. So what are the steps? The steps are, firstly we will find the dimension of the footing, like the width has already been given, but we will have to find the length of the footing according to the area of the footing, which is calculated by the load, total load. Net upward pressure will be calculated. Next the x bar, that is the x bar distance, the distance of the CG will be calculated. The shear force diagram will be calculated by this. Next is the zero shear force we will find, and the bending moment calculation will be there, right? Next, point of counterfracture, that is the point of zero moment, where the bending moment is zero, the point of counterfracture will be there. Then firstly we will design a footing slab. This footing slab will be designed, right? So area of the main steel and area of the distribution steel will be found. One-way shear check for the footing slab will be done. Next is the design of the beam. The beam is there, we have to design the beam. We will calculate the depth of the beam depth will be different. Then the design of the beam according to the bending moment, where the tension in this portion AB portion, tension is in the bottom portion. In this portion BC, the tension will be in the hogging portion, that is the negative bending moment. So we will design it accordingly. So BC portion, next is the CD portion. Finally the shear check will be there and the shear reinforcement for the beam will be calculated for this. And this is the detailing part. You will get the detailing of this beam and the section detailing will also be given by this Excel sheet, right? So let's start according to our problem. Design a rectangular slab beam type combined footing having a column size this much, load is this much. Column B is having a size is this much and the load is 1200 kN. Both the columns are 4 meter apart and the width of the footing is restricted to 1.8 meter. Safe bearing capacity in this case is 180 kN per meter square and FCK is 25 and FI is 415. So let's start. FCK in our case is 25, FI is 415. You have to fill your data in these pink cells only. Bearing capacity is 180 in our case, 180 kN per meter square, and center to center distance is 4 meter apart. Column A data is 300 by 300, right? You have to see this figure, 300 by 300, and column B is 400 by 400, right? 400 by 400. Working load for the column A is 800 kN and for column B is 1200 kN. Now we have filled the data. Self weight of the column 10% of the working load. 10% of the working load will add up, and this is the total working load, and this is ultimate working load, right? Factored load. So total working load from column A and B is 2200. This all will be add up, right? Next is the required area of the footing. Total working load divided by the SBC, safe bearing capacity. So this much is the area is required. We have given the width is 1.8 meter. So width is restricted in this case. So L is calculated as 6.8. So we have chosen the higher value. So we can choose 7.0. So 7 meter is the length of the footing and width of the footing is 1.8 meter. Now next, net upward pressure, you can see that total load upon AG provided, that is the area of gross area provided, is been calculated 158.75. Load per meter width, we will multiply it by the width we have given, that 1.8 meter. So 285.71 is the load in upward direction, right, per meter width. So projection is being calculated. X bar, that is the concept behind this design, that the CG of the column load and CG of the footing should coincide, right? So distance of this X bar from this A is being calculated as 2.40 by this formula, W1 into X1 into W into X2 upon W1 plus W2. So X bar is calculated as 2.40. distance of column A from the edge, that is A1. The projection A1 is calculated 1.10 by this formula, L by 2 minus X bar. So this is L by 2, this is 7 meter, this is 3.5 meter, minus X bar we have calculated, this is 1.10, and finally A2, that is projection 1.90, because this much is 4 is given as the distance between the columns, right? So projection has been calculated, shear force already been calculated, shear force left of A, shear force right of A, right? So it is negative direction, so in downward direction. So shear force diagram is being calculated. Point of zero shear force, maximum bending moment will be there, right? So at a distance 1.70, it has been calculated the zero shear force. So bending moment calculation, bending moment at A, at this point A, W into A1 square by 2, W is your this much 158 into A1 square, this is the projection by 2. So moment is calculated, MB, that the moment is calculated, W into A2 square by 2, and the maximum hogging moment, taking moment about the point C. So 240 kilonewton meter is the moment, right? Find the point of counterflexure, this point of counterflexure, because if you take a moment about E, then this is the quadratic equation, and where the constant A, B, C is being calculated, and y1 and y2, two values will be there for quadratic equation. So y1 is 4.10 and y2 is 1.50. So the distance will be 2.59. This is L0. Later on we will use the L0 value, that is the distance between the point of zero moment. Now we have found out the length and breadth, the projection of the column, shear force diagram, and bending moment diagram. Now the design of the footing. For the design of footing, we know that the critical section for the movement will be, this is the section, and the critical section for the movement will be at the face of the beam. This is the beam, right? This is the footing and this is the beam. We have to notice that the maximum size of the column will be taken as the size of the beam. So in our case 400 by 400 is the maximum, so we will take the 400 mm is the size of the beam, and this is 1.8 meter minus 0.4 divided by 2 will give you Lx value 0.7 and in both sides. So W into Lx by 2, W is 158.73 already been calculated, into Lx square by 2, 38.89, ultimate moment 1.5 times. So B is 1000 mm. So for this is the formula, mu limiting 0.138 FCK BD square. So we have to choose for Fe415 138. So D required is 130. If we choose for shear consideration, if we choose 260 as the D provided, so there is the increase the depth is required for the one way shear check, because it is fail in the one way shear check. If we take 300, so let's check, increase the depth is required. If we take 340, now okay, safe in shear. So we have to choose accordingly if it is safe in shear or not. So 340 is the effective depth we are going to provide. Clear cover is 50 mm in case of 50 mm in case of footing, and assume bar dia if you are assuming 20 mm dia. So overall depth is 400 mm by this formula, right? So overall depth we have calculated 400 mm. So area of main steel, ultimate movement is 58, already been calculated. PT is being calculated by formula in IS code. AST required is this much, AST minimum we have to calculate, we have to take the maximum value 480. If you choose 12 mm dia, you can see that the spacing required is being calculated. Rules for spacing 3D 300 mm spacing calculated, whichever is lesser is 232, and spacing round off is 230 mm. So AST provided is 491.48, AST required is 487, and we have provided 491.48. So PT provided is 0.145. So 12 mm dia, 230 mm center to center along the shorter span, right? Along the shorter span, this is the shorter span. So along the shorter span it is 12 mm at the rate 230 mm center to center. Area, if you change the value like 16 mm, so this much is the spacing is required, right? So we choose 12 mm, right? For the area of distribution steel, this much is the area required. We have, by this rule of spacing is there, 8 mm 100 mm, which is ever is there 100 mm center to center along the longer span, right? So next is one way shear check, already been done. One way shear check, the critical section for the shear at a distance of d from the face of the beam. So we have chosen a small d is 340 mm, 0.34, so balance is 0.36, so width of shaded area is L is 360, shear force W into L, W is 158 into L, 0.36, 57.14, the shear force, ultimate shear force is 1.5 times V, tau V is VU upon BD, it comes out to be 0.25, right? So from table 19, okay, this much is the area of the steel provided, percentage of steel 0.145, 0.145 lies between 0.15, you can choose according to this drop down 0.15 or 0.25, and in case of M25 this value for 0.15 this is 0.29 and 0.25 this is 0.36. You have to put in this pink cells. So by interpolation it has been calculated as 0.29, so it has been automatically 0.29 will be there, right? So this is okay or safe in shear because tau V is less than tau C. So in case of footing, tau V should always be less than tau C value. If it is greater than tau C value, then you have to increase the depth we have provided, right? You have to increase the depth, so it will be safe in shear. Now the design of the beam. So the beam concept is there. This is the longitudinal section of the beam and these are the column loads. So how the beam will deflect like this, right? The tension in this portion, AB portion, tension will be in the bottom portion, and in the middle portion, BC portion, the tension will be in the upward direction. So if you take a section, in this case the neutral axis, the tension will lies in the flange area, right? So in AB and CD portion, tension lies within the flange, therefore design it as a rectangular beam. So AB portion and CD portion, tension in bottom portion, that is it is in the flange. So this is the web portion, so that it is designed as a rectangular beam. And in case of this BC portion, tension in the upward portion, that is tension lies in the web portion. So mid portion tension lies with the web, therefore design it as a T beam. So B will be, in this case, B will be the effective width, that is width of the flange. So firstly we will design the beam and calculation of depth. So calculation of that, the bending moment diagram, we will see the bending moment diagram. This is the bending moment diagram. So maximum bending moment will be taken for the depth calculation, right? So it has taken 515.71. This is the ultimate moment. B is 400 mm in case of beam. So 415.138 is the coefficient, 748 is mm is the D dash. We will treat it as a D dash. Effective depth in case of beam for shear consideration, if we take 750 mm and 50 mm clear cover, so total D dash is 800 mm, right? So in case of AB portion, we are going to design AB portion. So bending moment of AB portion is 172.86. You can see that this is 172.86. Now this is MU, ultimate moment, for which we have to design. Effective depth we have 750 and overall depth is 800 mm. PT required is 0.34, AST required is this much. All the formulas have been inserted here. Minimum area is 384, so we have to take the higher value. So if you choose 20 mm dia, so 20 number, 4 numbers are required for the AB portion in the bottom portion, right? For the BC portion, we have already explained here. For the BC portion, tension lies in the upward portion in the web area, so it will design as the isolated T-beam. So for isolated T-beam, IS code has given us the formula L0 upon L0 by B plus 4 plus BW. What is L0? I have already explained you the point distance between the point of zero moment. This is L0. So L0 is calculated y1 minus y2, 2.59. 2.59 is the distance between the point of zero moment. So L0 value is calculated 2.592. Width of the flange B is 1.8 meter, BW is 400 mm, and by this formula effective width of the flange is calculated as 877. So bending moment at the mid portion by this bending moment diagram 240. Ultimate moment effective depth will be the same 750 mm, and overall depth is 800 mm, 0.21%. Area of steel is that much, 1378. So area of steel is required is maximum of these two. So if you assume a dia again 20 mm, so 20 mm 5 numbers are required in the top portion, right, in the middle, because there will be the hogging, so negative movement. So top portion 5 numbers of 20 mm bars are required. So this is clear. Next is CD portion. In the CD portion same sagging is there, so this will be designed as a rectangular beam. So in this case the moment is 515. You can see the bending moment diagram. This is the 515.71, 515.71, and this is the ultimate movement. Effective depth is same, 750. PT required, AST required is this much. This is very much greater, so we have to assume a greater dia. If you assume 32 mm, so 5 numbers are required in the CD portion, right, because of the greater dia. So shear check will be done. V is the maximum shear force. You have to check the shear force diagram. We have already calculated shear force diagram. In this the maximum shear is 657 is the maximum shear force. So it has already taken that 657 is the shear force. Ultimate shear force is 1.5 times 985. So tau V is 3.29. For M25 the maximum shear stress we have to check tau C max. So tau V should not be greater than tau C max in ideal condition. So if we take this is 3.1, so this is unsafe, increase the depth of the beam. So if we have taken the depth is 750, it is not satisfied, we have to increase it. So if we take 800 mm, then we will check this is safe in here, right, because tau V value you have to increase the depth, so tau V value will be reduced, so tau C max is satisfied. So tau C max should always be greater than tau P, right. Next is shear reinforcement. You have to take a maximum shear force, that is 985, ultimate shear force. Tau V is 3.080. Maximum AST provided is 40919. This is the maximum reinforcement we have provided, right, in CD portion. So PT provided is 1.26%. Okay, from table 19 we have to see 1.26 lies between 1.25 and 1.50, right, and the value is 1.25. this is 0.70 and 0.74. so this is 0.70 and this is 0.74. so interpolation, this value tau C value is calculated 0.701. so shear bars are required because tau V is 3.080 and tau C is 0.701. so tau V is very much greater than tau C, so we have to provide the shear reinforcement. So VUS is calculated by this formula, 761 kilonewton. If you assume 8 mm dia and 4-legged stirrup, you can see the ASV required is 200 mm by this formula. SV required, the spacing required is 76.23, and the rules for spacing is maximum spacing as per IS 456 is 300 mm, 0.75D 600 mm, SV minimum is 453, and SV calculated is 76. So minimum of these is 76 and round off value is 70 mm. So provide 4-legged stirrups 8 mm at the rate 70 mm center to center. So we have all designed the shear reinforcement also. So now you can see longitudinal section of combined footing. These are 2 columns. So in case of slab, we have designed it as 8 mm 100 mm center to center in the longer direction. These green portion is longer direction steel, and in the shorter direction we have designed it as a 12 mm 230 mm center to center along the shorter span, right. And for the beam portion, this is the beam, and beam this is the slab and this is the beam. In beam portion, at the AB portion we have, you can see that 4 numbers 20 required in the bottom portion, 5 numbers are required at the top portion throughout, and for the CD portion this is 32 mm 5 numbers are required, and this is the same, right. So friends, if this is the spreadsheet, we have designed the beam slab type combined footing. If you change the value like center to center distance between the this much, now you can see that all the values of projection has been changed, shear force calculation has been changed, the point of counterflexure has been changed 4.49, the values has been changed, right. So if you change the dia, you will find out that every value will be changed accordingly. So friends, this is the spreadsheet to design a combined beam slab type combined footing, and this is very quickly and accurately you can design it. And if you want this Excel sheet, please WhatsApp me, and if you like this video, please subscribe this channel for more design videos. Thanks for watching.